Hi everyone. This part two of the video with regards to the consumption savings framework, the two-period consumption savings framework with the presence of a credit constraint. So in the first video, what we did was we basically solved for the consumption allocations as well as calculated what would the consumption allocations be in the presence of a really binding credit constraint wherein the consumer is not allowed to have a negative balance at the end of period one. So today we just continue with the questions that we've had. So we answered A and B in the last video. Now let's answer C. C is asking, does the introduction of this credit constraint enhance or diminish welfare? And what we do for that is, well, we're given with a direct utility function and we know the allocations under both cases. What we can do is simply calculate for the level of utility and compare the two. So that's what we do with C. So for C, so recall without the credit constraint, we had that C1 star is C2 star is equal to 7.9. With the credit constraint, we had that C1 star is equal to Y1 is equal to, in this case, 6. And the C2 star is equal to Y2 is equal to 10, right? So if we calculate for the utility under the unconstrained case, 7.9, 7.9, well, you know that the utility function, C1, C2, is square root of C1 plus beta square root of C2. Well, just use that form and plug in the values. So you get square root of 7.9 plus beta is 1 over 1.1 times square root of 7.9. And this is approximately 5.37, right? And if you calculate it with the credit constraint, that is using the new C1 and C2, that's 6 and 10 basically, we get a square root of 6 plus 1 over 1.1 square root of 10. And if you calculate that, that is approximately 5.32, right? So clearly, welfare diminishes. And that's to be expected because you're forcing the consumer to not borrow in the first period, whereas if you look at the unconstrained case, he would have borrowed under that case. So clearly welfare diminishes. Okay. Now, what about D? Okay, D is basically asking, okay, what is the effective real interest rate of the consumer subject to the presence of the credit constraint? Well, that's sort of simple to calculate. What we need to remember is that MRS, under the optimal conditions, based on the first order necessary conditions, should be equal to 1 plus R, right? And MRS is basically use 1, C1, C2, divided by U2, C1, C2, the derivatives, and that should be equal to 1 plus R, right? So how do you calculate U1, C1, C2? Well, you just derive the utility function with respect to C1, and you do that, you get 1 over 2 square root of C1, right? And U2 is similar. You derive the utility function with respect to C2, and you get beta divided by 2 square root of C1, right? And then what you do is you divide the 2, so you get a 1 over 2 square root of C1 divided by beta over 2 square root of C1, C2 rather. C2 is equal to 1 plus R, right? And basically this one will be equal to 1 over square root C1, 2 times 2 square root of C2 over beta. And the 2's will cancel out and you get square root of C2 over square root of C1 times beta is equal to 1 plus R. Therefore, square root of C2 over square root of C1 beta minus 1 is equal to R. That would be our real interest rate. And what we do is we just sort of plug in what we have. What we have is square root of 2 under the credit constraint case is equal to Y2, so that's 10, divided by square root of C1, that's equal to Y1, so this one will be equal to 6, times 1 over 1.1 minus 1 is equal to R. And if you solve for that, R is going to be approximately, okay, 0.42. Right? So that's going to be the real interest rate. Okay. Now, the last item is basically if the consumer, okay, experiences a temporary increase in the real income, okay, what would happen? Well, this is sort of just an extension of letter A. So if you recall, okay, we were able to derive, okay, this formulation here, this C1 formulation. All we need to do basically is to involve, okay, basically write it in terms of the new values. Okay, so we know, okay, that so E C1 star is equal to 1 over 1 plus beta squared times 1 plus R times y1 plus y2 over 1 plus R. But we now have y1 being equal to 10 instead of being equal to 6. So if we plug in everything, so that's plus, this is 1 over 1.1 squared times 1 plus R is 1.1 times 10 plus this one will be y2 is 10 also, no change in the incoming period 2, divided by 1.1. And if we simplify this, this and this will cancel out, right? And we get 1 over 1 plus 1 over 1.1 times, okay, we can factor out the 10 here. Both of these terms have a 10. So 10 times a 1 plus 1 over 1.1. And clearly these two will cancel out. And therefore we have that C1 star is equal to 10. And because we know that the Euler condition holds true, right? So why is that the case? We know that C2 is equal to beta times 1 plus R squared C1. But beta is 1 over 1.1. And then 1 plus R is 1.1, right? Square C1. So this one will be equal to 1. So C2 should be equal to C1. Therefore, C2 star is also equal to 10. So that ends our video on basically our series on the consumption savings framework with the credit constraint. We can see that in general, if we impose a harsh credit constraint on the consumer, it is welfare decreasing. And we also see how changes in nominal incomes nominal incomes can affect the consumption allocation as well as how to calculate the real interest rate. So thank you for your attention, and I'll see you in the next video. Thank you very much.